In this video, I'm going to go over a classification problem using a very famous dataset called the Titanic Survivor Dataset that's publicly available on Kaggle. A quick overview, it has the following attributes. So survivor, so whether passenger survived one or not for 0. Ticket class, again here, whether first class, second class, or third class cabin. A sex, male or female, the age of the passenger in years, again, siblings or spouses on the Titanic, parents or children, the ticket number, passenger fare, cabin number, and the port of embarkation, denoted or abbreviated as C, Q, and S. Okay. Also, we're going to be using some of the top classification algorithms like decision trees, random forest, naive Bayes, KNN, SVM, and neural network. To start us off, we're going to load the following libraries. Again, if you don't have these libraries, you can just uncomment that, use this function install.packages, and then in one single line of code, you can type all this missing, depending on whether you already have it. You can just use this, the way I have already typed it here. Okay. All right. Since I already have that, so I'm just going to use the library here to load the tidyverse for data wrangling. We've already used this a lot. Manipulation, caret. Again, we're going to use this for model evaluation, especially generating the confusion matrix. rpart, we're going to use that for decision tree, access the decision tree algorithm for classification. rpart.plot to visualize trees, random forest. Again, this one, 1071, we use it for naive Bayes and SVM. Double K, double N for K nearest neighbor, neural net. You can use for neural network, or alternatively, you can use the NN, double N net, right, for neural network. Again, you just have to make some modification in the code of how you access that algorithm. Okay, and lastly here, we're going to use the here package, a very simple and fast way to reference your files from your current directory, especially if you have some relative path, kind of nested in your folders. All right, so I've already loaded the Titanic dataset. So using the read.csv that comes from the tidyverse package. Okay. So let's go ahead and view the first 3 observations from our dataset. We can see we have the following columns, right? Okay. Again, here we want to view the structure of the Titanic dataset, and we can see we have 891 observation and 8 variables, right? And we can see the data type. So here, survived actually is a factor. Okay, so I might just need to load it back again. So I'll just rerun this again. So load that again over here, then view the first 3 observations, then view the structure here. Again, now we can see the data types for all these different. So we have 12 variables. This is the raw data set. We can see we have different data types here. So during data preprocessing, again, for classification, we might need to, convert this to a factor, right? Especially if we find it that it's useful for our use case. Okay. So the next step, I just threw in here so that we just view the frequency table, or the frequency, the bar plot of, those who survived and those who didn't survive. So a quick breakdown here. So here, the first thing here is that this code over here just creates a table, okay, a frequency table of the values in the survived column, okay, and this information contains whether the passenger survived with 0 or 1 for those who survived, right? And then when we combine that with the bar plot function here, all right, So again, the bar plot just creates, or rather this function creates a bar plot of the frequency in the table we've just created inside here as the argument, right? Again, the bar plot here, the height of each bar just represents the frequency of each value, whether it's a 0 or 1. And then this argument here just tells us the labels for x-axis, all right, which represents the possible values of the survived column. And then the main here is just, we just set the main title of the plot. So I run this and we can already see here a visual representation for that. All right, so let's move on. So the first thing you want to do once you load the data set as part of data preprocessing is just to check whether you have missing values, right? So a useful function here is to use the call sums, right? So here, again, here, Titanic is just our data frame or data set, okay? So this is NA, Titanic just returns a logical matrix, okay? And this matrix should have the same dimension with your data frame. So for example, here, if I do dim Titanic, right, we can see that it has this kind of dimension, right? So it'll return a matrix, right, that a logical matrix that contains the missing values. So here we'll return whether it's true, indicating missing values, and false, right, for non-missing values. Okay. However, when we combine now with this function here, call sums, so the call sum just takes this matrix of logical truths or false and returns a vector that contains the sum of the true values. The true value here will correspond to a 1 or be treated as a 1, and false as a 0. So the sum here will just return the count of all the missing values in each column. Okay, so when I run that, you can see now it just returns a count of all the values in each column. Similarly here, we can also use this function here. So again, the sapply here is just a function that we specify, right? It takes 2 arguments. Again, we can see here, Titanic is the input, is our data frame, is our data set. And then we have this function over here, okay? So this is just a function that takes a vector input, x, right, and returns the missing or the sum of the missing values in that vector. Okay, so again, this function just applies to all the columns in the Titanic data set using now the sapply. We've already seen this before. Okay, so again, if I run this, you can see it just returns the same thing. So depending on your preference, you can use either one of these. Okay. Now that we've done this, another thing is now we want to replace the missing values. So we can see we have a lot of missing values in the age column, right? So one method, we've already seen this, we can impute the mean here. Again, we can impute this by, using the median, right? So the median of the age column. All right, so the first thing here is to, what we're interested in the specific column. So from this data frame, we want to access the age column using the $sign. Then we subset, again, we want to subset, only those values that are missing, or rather that have NA, right? So we use is NA. So we want to return only the values that have, or rather the missing values, right, is NA, okay, equals to true. Okay, then on this right-hand side, we want to get the median of the that column, Titanic age. So use $sign to access this column, right? Okay, and before we find the median, we want to remove all the, so first of all, we want to remove all the missing values, because you can perform this arithmetics or statistical summary when you have missing values. Okay, then once we get that, we assign this to all this on the left hand side. So essentially we're going to replace the values of all these missing values, right, that we already subset, okay, with the median of this age column. Okay, and then over here, just going to explain this, the rest is just the same. So here again, as you can see from our structure here, we had things like cabin, impact as character, So essentially here, we want to replace everything that is a character to a factor. Okay, in classification problem, most of algorithms work with discrete values. So very important, or factor, especially in R. So here, so essentially here, you use the factor here. We just want to convert this into a factor. So we just access the data set and we specify the specific column. So we want to replace this. We want to replace, again, overwrite the survived column here, okay, with a factor, okay. So once we do that, we replicate that for all those that have characters. So again, we run that. And then lastly here, we want to remove the irrelevant columns. So we don't think this will be appropriate for classification for passenger ID, okay. We can remove the name, again, ticket, and cabin. Okay, so to do that, we're just gonna use we just say from our data frame or data set, we use this pipe operator from the dplyr package, use the verb select, then we use the negative sign here, then we want to subset, right? So we want to exclude or remove all this, right? We use this C to just concatenate all these columns, and then again, just update our Titanic dataset here, okay, to exclude all this. Okay, so once we run that, we can use the glean function here. Gleans is a very useful function that provides us a quick summary, very neat summary of our data type and some examples of observations. So we can already see we've converted some of these columns into factor. Again, we just left those that double to remain as double, right? And you can see we've already excluded what we don't need. Okay, so we are done with data preprocessing. The second step is to please split the data. Okay, so this is a very important step before you perform data modeling, right? So to do this, we're gonna use this. So first of all, the set seed here. Okay, so the set seed here just is a very useful function that allows us to maintain reproducibility, because it just allows you to set the seed for random number generator in R, right? The number 123 can be any value. Again, can be a non-negative integer, right? So this is very useful, especially when you're working with statistical models. These models could be, involve random elements such as cross-validation, could be bootstrapping or Monte Carlo simulations and whatnot. Okay, anyway, so the first thing here we want to do is to split the data. Okay, so to split the data, we're going to use this create data partition. Okay, this comes from the caret package. Okay, so this just creates a stratified random sampling. Okay, if you recall, we talked about this, especially when we talk about cross-validation, which I'll talk a little bit more about that. But again, it just creates a stratified random sample, right, of the data. So again, here, we'll just return a vector of indices, right, that's used to subset whether the training, subset the training and the test sets. Okay, now, so the argument here, so we are interested in the class column, right, the outcome variable. Okay, so we're gonna be subsetting based on this survived column, right? So this is where we're gonna apply the stratified sampling. Okay, again, so we stratify the sampling here. We just want to make sure the proportion of the survivors and non-survivors is similar in both training and test set. Okay, and then the P here just means the proportion here is going to be 70% for training, and then the remaining one, 30%, automatically will be apportioned to the test set. And then the list equals to false here just means that we want to return a vector of indices rather than a list. Okay, so once we have that, the next thing is to store all this into train index. And then we subset this. So we just want to subset data set here, and we're saying we want to apportion, only rows from the train index, right? we want to store that as train, and then the rest, anything that is not the train index, which is just the test data, we just apportion that to the test. Okay, so that's exactly what's going on here. Yeah, and this is how we're just going to be splitting the data into training and test set in R, right? So essentially, we just subset from the training index, we subset the required Titanic data frame that excludes the rows specified by the train index, put that in the train, and so on and so forth. All right, now that we have our train and test set, 70% and 30%, we can always change this value to 80, 20. Again, so we can begin by looking at decision tree. Okay, so the first thing we're going to do here, we've already explained the set seed. So here I'm just going to use cross validation, right? So here we're going to use the train control function. Okay, so this comes again from the carrot package. We use this to train a variety of machine learning models, right? So it takes the following arguments. So the first argument here is method. We specify that we want to use cross validation. Again, this is a resampling method. We've already looked at this. If you recall, cross validation simply is just a technique. You know, we divide the data into different faults, right? And then we train this model on all but one of the faults, right? And then we test all the remaining fault. Okay, so we repeat this process, okay, for each of the fault, and the resulting we get the results and average that. Okay, and you know, this allows us to just get a more robust estimate of the model performance. Okay, the number equals to 5 here is just specify the number of faults that we want for a cross validation process. Okay, so in this case, we're just going to be using a 5-fold cross validation, which means we're going to divide the data or subset the data into 5 equally sized partitions, right? And model this model will be trained and tested 5 times. Okay. So again here, because we're going to be using the cross validation, we're going to use this function called train. Okay, so this function train just allows us to pass a number of so we're going to just pass a number of arguments over here. So the first argument here essentially just tells us that so this is actually the formula, right? This specifies the dependent variable, which is survived, and we want to regress that with the independent variable, right? All the variables. So when we use the tilde here and then a dot, we just say we want to, show the relationship, apply this formula for dependent and the independent variables for all the variables in our train data set that we already partitioned here. Okay. And then we want to say that we want to get this data, okay, from our trained data set. Okay, so this way we're going to extract variables, whether dependent or independent. Okay, again here the method here is rpart. Essentially, we're telling R that we want to use decision trees. Okay, again, so these are very important parameter. And then the train control here is just a function, or rather it's a parameter. You know, we just tell R that we're going to be using the fit control. We've already specified this. We're going to use cross validation, and we've already specified that previously. So once we have that, again, we store that in our model here. Okay, and then the next thing is to predict the outcome for our test set. Okay, to do this, we're going to use the predict function. Okay, so this predict function, we use this to make the prediction on the new data. Okay, so it takes 2 arguments, or it takes our model that we already defined here, and then we specify our new data. So our new data here will be our test data here, the unseen data. So we just want to fit our model here on our new our test data that our model has not seen before. Remember, we trained this, we fit our model using train data. So now we're going to use the predict. Okay, again, so we store this as predict dt. Okay, so once we have that, so this would just be a vector of predicted class labels. Okay, where each element will correspond to a row in the test data. Okay, And then now we're going to calculate the accuracy precision recall using the confusion matrix function. Okay, so this function here again comes from the caret package. It takes 2 arguments. So we take now take the vector predicted class labels that we generated previously here, again using the decision tree model, right, as a reference, right? And then again here we want to compare now. Okay, we want to compare with this column here, okay, from our test data. Okay, so we want to compare the predicted values, right, with our or rather this the predicted values with our sorry, this is the actual values with our predicted values. Okay, so this will generate a summary of contingency table, a confusion matrix. We're going to see that, and then from there we can generate all these different summaries, right, like precision, recall, F1 score, and so on and so forth. Also, I threw in here this rpad.plot just to see, how this decision tree kind of visualizes that. So I'm just going to run this. You can see here, again, we're able to generate some of the accuracy. We can see here the accuracy for this decision tree is 75%. Okay, and this is the decision tree for the Titanic dataset using the visualization for the tree for decision tree. And you can see here, essentially here, we just want to use from our model, we're going to use the final model. Just tell R that's going to be a final model. These are just parameters that control the amount of information we're going to see here, the size, and so on and so forth. And then this is just the title. Okay, and that's it as far as decision tree is concerned. So next, we're going to look at random forest. So again, we just repeat the same process. Again, here we just create the random forest model. This is our formula. So we just want to create a formula, or rather, this is our formula here for dependent and the independent variables, and we are getting this from the train data. Okay, once we have that, we use the predict function, we pass our model, random forest model, and then we kind of, fit that on our test data. Then we generate the confusion matrix comparing the predicted values with the actual values, right? So we print that. You can see we created a confusion matrix here, and you can see here, so we already have some reference here. Okay, so we can see here, we kind of predicted those who survived, and they were actually 69, and we misclassified 21. Okay, again here we got 143, and so on and so forth. Again, we can see the total here was 164, and again here is around 102. Okay, for the total. Anyway, so we can see here the accuracy is much higher than the decision tree. Again, if we go back here, again, we have that, and so on and so forth. We can see the recall here was actually much higher, 87.2. Okay, for decision tree, actually 89%. So we do again for naive Bayes. We repeat the same procedure. Here I decided to use cross-validation. Again, we just use the train function. We pass our formula here, dependent variable. We regress that for all our independent variables that comes from the train data. The method we're going to be using here is naive Bayes. The train control or TR control here, essentially, we just want to, use the cross-validation that we already kind of specified previously over here. Okay, cross-validation 10-fold, right? So once we have that, again, we do prediction, use the predict function, use the confusion matrix to evaluate our model, right? So the output looks like this. Again, here the accuracy kind of dropped a little bit. Okay, based on cross-validation, it looks like naive Bayes doesn't do very well cross-validation. I'm just gonna change this a little bit. So I'm just gonna do that without cross-validation. So let me try that again. So if I do this again, the accuracy goes up, right? So you just want to use this with a lot of caution. There are those which you will see some improvement when using cross-validation. But again, cross-validation, if you remember, is just another technique that helps us to mitigate overfitting, right? Remember, you're trying to balance the bias variance trade-off. Okay. All right. So again, this is another code that you can calculate the accuracy, precision, recall, and F1 score of a model. So again, this just takes the we just access the accuracy, precision, and recall, okay, from predicted probabilities for naive Bayes. So if I run that again, we just extracted what was here. And again, we can see for accuracy, again, this is, let's see what we have here. So you can see we have 70% here, 70% over here. Recall again here is 88% shown as sensitivity. F1 score 78%, and so on and so forth. So this is just another way to explicitly access. This overall here just means you get the mean average of your accuracy, and then this is just by class, the positive predicted value, sensitivity. You can pass here F1, so it just allows you to access the specific parameters from the confusion matrix. Okay, for support vector machine, again, we do the same thing with cross validation. The only thing here we're going to change here is we're going to use the SVM radio. What that means here is just going to use the kernel function. The kernel function is very good, especially if you're dealing with nonlinear function. It's a little bit more robust. So again, so just keep that in mind. In fact, something else I just need to add over here. This function, kernel function, is just a mathematical function. Okay, so once you start looking at neural networks, you see how to use the kernel function that just allows to transform the data into higher dimensional space. If you recall, SVM is very good in creating a hyperplane. We've already seen this in our lecture, where you can linearly separate different classes using a hyperplane. So if that is the case, SVM might be a good choice because it implements this kernel function. Okay, and this can have an impact on the performance of your model. Okay, again, a kernel function just allows you to capture some complex nonlinear relationship between variables in your data. Okay, so we run this again, and you can see here we have 75% accuracy, or rather 78% accuracy here. Again, don't worry, we're gonna just do a summary of all this. And lastly here, we also have KNN here. Just gonna again use the train here for cross validation. This is our formula. Again, remember, you can be explicit here. We don't have to use tilde and dot here to mean everything from the train data. You can actually regress this. I've done this using the neural network. You can see you can regress this and just use the plus sign to just specify the specific, explicitly specify the specific columns or variables that you want to select. Okay. So again, here the method is KNN. All right. So the same remains for predict. Predict the model, the test data, use confusion matrix to evaluate the predicted values and the actual values. So we print that, and we can already see that KNN is not performing very well using cross-validation. Then lastly here, we're going to use the neural network. Okay. So the neural network here, we're just going to, load up our data again. And then we're going to use the structure just to view the structure of our data. So again, why I decided to do this is because when using the neural network, it works very well. So you might want to chain all this into numeric, right, or discrete values, because neural network really work well with values. Okay, it could be numeric values or discrete values. So we're going to perform some data preprocessing. So to do this, again, we already know that we have missing values in age. So we want to remove that to limit, to improve the performance of our model. Okay, so we're going to use the dplyr package. So again, here, we're just saying from our data set or from our data frame, use the pipe operator. We're going to use the mutate function. So mutate, again, here, we either create a new variable entirely or just replace, overwrite the values of our variable. So in this case, we are interested in those missing values, right? Those missing values in our variable age. Okay, so from this data frame, okay, we're going to use mutate. Again, we're just going to use the age. Again, we replace that with the contents of this, right? So this time around, we're going to use the mean, right? So here we're just saying if else, just allows us if else. So we just want to check, right? So we want to check if we have missing values, right? If we have missing values, then we want to apply this function. Okay, so again, here we just want to get the age, the mean from our age column from the Titanic dataset. Okay, and then before we do that, we just want to make sure that we remove all the missing values, right? Again, we just want to replace the contents of age. Okay, so we replaced all this and we overwrite what is already here, okay, for all the missing values. Okay. Secondly, here, I just added this, especially if you're using the test.csv that comes from Kaggle. Again, it might have a few, missing values. So this is how to do it. You can just, if else, you can replace with s, for embacked, for those missing values. Okay. So once we have that, we're gonna use again, we're gonna use again here. We want to deselect the irrelevant variables. Okay. So in our case here, again, we just want to say from our Titanic. So we're going to use this again that we've already pre-processed. So this is why the piping is very important. So I just say from this data set here, then we want to select, okay. However, here we're just going to use the negative value. So we just want to remove this from our data set. Okay. So once we remove that, then we want to mutate, okay, the sex. Okay. So we want to record this, right? Remember, sex here was character. So we want to take care of that. Okay. So if else sex equals to male, then replace with 1. Else replace with 0, because we only have 2 values. Okay. Similarly here for embacked, right? So once we remove the missing values, so we just want to say we know we have SC, we have 3 values, right? So for the first one, we just say where we have S, replace with 1. If else, where we have C, replace with 2. Anything else, replace with 3. Okay. So we run that. Again, we partition here, just going to use the 70%, 30, 70% for training. The rest will be 30% for test. Okay. So we run that. In fact, here, if we just going to use glimpse here, glimpse. So glimpse, so we can just going to, what we have here, let's just use structure here for our Titanic dataset. Okay, this type. So you can see here, we've replace this, or rather we've changed this to number. Again, what we have here, actually TF. Okay, so here, because this is our transformed data set, so we can see here we've removed what we don't need, and we've changed this to number and age to number. Okay, this works very well with neural networks. Okay, so once we split our data into 70-30% proportion, the next thing is to train or to fit our formula. So we want to fit the whole of this. Yeah, so essentially here we're saying this is our dependent variable. We want to regress this on all these independent variables, right? We're getting this. In fact, here we are getting this from our, train data set that we've already pre-processed. Okay, hidden here just means we're going to be using 2 hidden layers. Each of these hidden layer has 5 neurons, right? The step marks here essentially just tells how many iterations are we going to run, a neural network. So essentially here, that's just 7 zeros, right? Could be 1 million or 10 million times. Okay. The linear output here just means, should we use an activation function? So in neural networks, we have several linear activation functions like sigmoid, tanh, ReLU, but in this case, we're just going to say false. Okay, so this usually is applied at the output. Okay, and remember the hidden here just appears between the input and the output in a neural network. Okay, all right. So once we have that, let's create our model. Comes from the neural network. Notice how it takes quite a bit because it has to do all those millions iterations, right? This is a feed-forward neural network. Okay, so it's just gonna establish or create a relationship between the dependent variable with all these independent variables, right? And tries to come up with a best fit, trying to create a relationship between all these variables so that now we can now use this to predict, okay, on our test data that we already have here. So our test data here is the 30%, okay? So, and this test here is our unseen data. So depending on the complexity of your neural network here, so essentially here, I could have changed this to maybe 3, which just means we have one hidden layer with 3 neurons, so you can configure this however you want, right? We can put another comma here, comma 3, and that means we have 3 hidden layers. Each of these have 5 nodes or 5 neurons, and 3 neurons. Okay, so you don't want it to be too complex for a very simple problem that might lead to overfitting. So a good balance should be good enough, and especially neural networks are very good, are known to be very good for nonlinear relationship because you can project your data into high dimensional space. Okay, so that's done. The next thing here, we're going to use the predict function to evaluate, compare our model with our test data. Again, we want to store that as predicted class labels. Again, here we're going to convert this into a binary. So we're going to convert into a binary probability. So essentially here we're just saying this is our threshold, right? So our predict here, remember, this is just contains the predicted class labels, right? So for these values, right, in fact, let me just do a head here for just to see what we have here. Pred, let's go NN, right? So we can see this is our predicted value. So we're saying here, this will be our threshold here. So anything that is less than 0.5, we treat this as 0. Anything greater than 0.5 will be treated as 1. Okay, so once we have that, then we can use our confusion matrix to create a table. Okay, so this table just creates a summary, right? A summary of the predicted variables, and we want to test this on the test dataset, right? And here positive just means that our class here is going to be positive. Again, so again, I'll just repeat this once more. So with this one here, we just predict the survival probabilities, right? For the test set using the neural network NN, right? That we already created. Again, so the second code here, so we use this just converts the predicted probabilities here. It converts this predicted probability using the if else, okay, into binary prediction by setting the threshold to 0.5. Okay, that means if the predicted probability based on this, right, is greater than 0.5, okay, it's classified as 1, okay, which means survived. Otherwise, it's classified as 0, meaning the passenger did not survive. Okay, and lastly here, we're going to use the confusion matrix, okay, to calculate the performance metrics of our model, using the accuracy, precision, recall, F1, right? Again, here, we already know that the positive class is for this problem is 1, which means that survived, okay? And the table here just creates a summary. So we run that and we can already see that we have a confusion matrix here. Based on that, we generate the accuracy. So you can see the accuracy is a little bit higher. And then lastly here, to summarize all our model performance, the first thing we want to do here is to create the model. So the first thing here, the model here is just a character vector, okay, of all the names of the models, like decision tree, random forest, naive Bayes, KNN, SVM, and neural network, right? And then the accuracies here, okay, accuracy, precision, recall, and F1 measure. Essentially here, these are just numeric vectors, okay, that contains the corresponding performance metrics for each model. So for example here, for DT underscore CM, so we want to access the, so we want to use the square bracket here to access the accuracy for DT, right? Similarly here for random forest. Precision, we're just going to use the by class here to access the positive predicted value, right? The same thing here, we just want to access these recall for decision tree. And lastly, we want to access the F1. And we do this for all the other models, okay? And then lastly, we use the data frame here, okay? Again, the data frame here where we pass our model, right? Then we pass now the vector. So remember, these are just numeric vectors, right? And then we summarize that, okay? So when we click on that or we run that, we can see create a nice summary of the tables with the extracted, confusion metric measures like accuracy, precision, recall, and F1 measure, right? So from here, we can already see, so we have neural network has one of the highest accuracy, followed by random forest. But if you look at it cumulatively with other recall confusion metrics, we can already see that random forest here performs much better on all the different metrics. Here actually is one of the highest. Here almost third highest, but here also it kind of performs very well. So random forest here already does a better job than all the other algorithms, okay? If we look at closely here, again, we can see SVM here did very well on recall, not so bad on F1 measure, very closely here on accuracy and precision. So in conclusion, we can already say SVM and random forest does a better job when you use cross-validation. So you might want to try without cross-validation, might get different result. But again, this, just take this with a lot of caution. You can always do a little bit more of other feature engineering techniques to kind of improve the performance of your model, okay? And with that, we conclude this classification problem using the Titanic dataset, where we reviewed all these different popular classification algorithms.